Okay, this is multivariable chapter 14.3. So the title is change of variables polar coordinate. So in this section, we basically transform the double integral from rectangular coordinates to polar coordinates. So just a little review. When we are changing coordinate, x goes to r cosine theta, and y equals to r sine theta, and r square equals to x squared plus y squared, and tangent theta equals to y over x. So this is just the basic rules we have to keep in mind. And here's a theorem that we need to remember. So double integral f of x dot y dA, this equals to alpha beta and another integral g2 of theta and g1 of theta, and we transform the whole f function to something like this, and we have to time an r back here. Have to keep that in mind. So where alpha and beta are the boundaries for theta, and g function of theta and g1 of theta is the boundary of r. So we can use this to integrate and calculate the area. Let's see an example here. So there are two circles. One is x squared plus y squared equals to 1, and another circle is x squared plus y squared equals to 5. And here we need to calculate the area have to integrate this and calculate the integral of this. So we just do step by step. First of all, we transform the boundary of theta, so it's 0 to 2 pi. It's a circle, so yeah. And the boundary for what's it called, the r. So 1 is this r equals to 1, right? And this r equals to square root of 5. So it's square root of 5 to 1 to square root of 5, and we just plug those corresponding polar coordinate variables in. Becomes like this, and dA, no, actually not dA, it should be dr d theta. Oh, here I made a mistake, because remember we have to times an r right here, so that's that thing we have to keep in mind. So right now we just need to solve this whole bunch of math, and the answer is 6 pi. So that's how you set up a polar coordinate double integral. And let's see another example here. Okay, so if we want to use double integral to calculate the area enclosed by this function, r equals to 3 cosine theta, 3 cosine of 3 theta. So if you graph that out, it's gonna look like a flower, like that. So we can get the area of this and times this area by 3, and then we'll get the whole area of this flower. So so the area, like 1/3 of the area of this flower should be this, right? And since the period is supposed to be 2 pi, but we times a 3 here, so it becomes 3 over 2 pi, and right now we only need 1/3 of it, so it will be pi over 6, and to the negative pi over 6. So that's basically this times 2, this times 1/2. So it becomes, wait, let me see, it becomes 6 over 2. So that's basically this range. And then for the r, the upper bound is this function, so we just move this over here, and the lower bound is 0, is this point right here, and there's no f of x and y, so we just times an r back here and dr d theta, and we solve this integral, and it will be 3 pi over 4. Yeah, that's 1/3 of the area. So if we want to get the whole area of this flower, it will be 9 pi over 4. That's how you solve a double integral using polar coordinate and get the area or the volume. Thank you.